Hello, and today we're going over particle physics for A-level physics. So let's get started. So first we're starting with atomic structure. So this is how an atom looks like. So here you have the nucleus in the center, which has nucleons, which are the protons and the neutrons. And in the shells, also in the orbit, you will have electrons in the orbit of around the nucleus of that atom. And for each particle, so we have the proton, neutron, and the electron, all inside the atom. The charge of the proton is plus, so positive, 1.6 times 10 to the minus 19. The charge of a neutron is 0, because it's neutral. And the charge of an electron is just minus of the 1.60 times 10 to the minus 19, which is the negative of the charge of a proton. And the masses of each, so as you can see, the proton and the neutron have very similar masses. So you have 1.67 times 10 to the minus 27. And the electron has a very small mass of 9.11 times 10 to the minus 31, which is a lot smaller than the minus 27. And then if you have relative charges and mass, you have the proton has a relative charge of +1 and the electron of -1, and then neutron still 0. And the proton and neutron have a relative mass of 1, and the electron has a relative mass of 0.0005, which is 1 over 2000. And the proton number is the same as the atomic number. So when they say the atomic number of an element or atom, they're basically referencing the proton number. And this defines what type of element the atom is. And if the atom is a neutral atom, then the number of protons is equal to the number of electrons. So the charge cancels out because you have the positive charges from the protons and the negative charges from the electrons. So if they're equal, they should cancel out. And the nucleon number is just the number of protons plus the number of neutrons. And it's also known as the mass number and is denoted by A. And the atomic number is denoted by Z. So if we put that all together in element notation, so as you can see in the periodic table, you have your A at the top, so your mass number at the top or your nucleon number at the top, and your atomic or proton number at the bottom, and your element symbol would be here on the side, where, for example, for carbon it will be a C, for oxygen an O, hydrogen a H, the symbols that you see on the periodic table. So now let's move on to isotopes and specific charge. So an isotope, the definition of an isotope is that it's an atom with the same number of protons and a different number of nucleons. So it also has a different number of neutrons. So this is the definition for an isotope. And for example, in hydrogen, you can have normal hydrogen, hydrogen 1, which has 1 proton in the nucleus, while deuterium is an isotope of hydrogen where you have 1 proton and 1 neutron, so you have a different number of neutrons as the first one, and therefore a different number of nucleons in total. So this is an isotope, and then you have tritium, which is another isotope where you have even more nucleons or even more neutrons inside of the nucleus of the atom. So different number of neutrons, it doesn't really affect the chemical properties of the element. So for example, hydrogen will keep acting like hydrogen in whichever combination, if it's deuterium or hydrogen or tritium, it doesn't really affect the chemical properties. It will still act like hydrogen chemically. However, it does affect the stability of the nucleus or of the atom in general. So an unstable nucleus is basically when it's radioactive, and they usually decay into different nuclei over time, which are more stable. So it tries to become more stable by decaying. And radioactive isotopes are very useful for finding the age of things. For example, in living things, we take in carbon-14 from the atmosphere, because the photosynthesis in plants or animals eating dead plants, they are constantly taking this carbon-14 from the atmosphere. But when they die, they don't no longer take in this carbon-14 because the plants are not photosynthesizing or the animals are not eating the dead plants. So the amount of carbon-14 would decrease over time because carbon-14 normally decays when you're not constantly taking new carbon-14s. It's just going to decay over time, so it's going to decrease. So you can find out the age of things by the amount of carbon-14 they have in them. And now, specific charge is a very important formula that they might ask you in the exam. Specific charge, if they ask you to find a specific charge, is just charge over mass in SI units, so Q over M. And this is just the formula for a specific charge. And now let's move on to the strong nuclear force. So the strong nuclear force is responsible for holding the nucleus together because it binds all the nucleons together. So the protons, because they're all positively charged, they don't repel each other away. So if there wasn't a strong nuclear force, the protons would repel each other and you would no longer have a nucleus anymore. So the strong nuclear force holds that nucleus together against the forces, the repulsion of the protons. And it has a very short range, and it has to be stronger than the electrostatic repulsion so it can hold the nucleus together. And it works pretty equally for all nucleons, so for both protons and neutrons, it has the same force, no matter if it's a proton or a neutron. And below a certain distance between the nucleons, so if the nucleons have a certain distance away from each other, if it's small enough, the strong nuclear force starts to become repulsive instead of attractive. So in this case, as you can see, is attracting the nucleus together, so it stays intact. But if they become too close to each other, it starts to repel. It's so that the nucleus doesn't crush into one point, into a singular point. And here's the graph of the strong nuclear force versus the electrostatic force over the nucleon separation. So as you can see, so say the positive is repulsion and negative is attraction in the graph. Between 0.5 femtometers and 3 femtometers, the strong nuclear force becomes very attractive. So this is where the nucleons would be separated at, so they would have an attraction. But as you can see, below 0.5 femtometers, it becomes repulsive, so it doesn't crush to a point. So if they come too close, it starts to repel, and then tries to keep in this balance so that the nucleons are held together, but they don't crush, but they also don't fly away because of the electrostatic force. And then after 3 femtometers, the strong nuclear force falls very rapidly because it has such a short range. And here's just the electrostatic force for comparison. So it has a larger range, as you can see, it just extends for longer. But it's repulsive always because it's protons against protons. And that's why you need the balance between the repulsion and the attraction, so you can have the nucleus all together in this region here. And if it goes too close, then there would be a lot of repulsive forces, so it kicks back and it would stay pretty stable in that position, so close together. So now let's move on to decay type. So you have your first decay type, which is alpha emissions, and they happen in very large nuclei when they are too massive normally for the strong nuclear force to be stable. That means they have too many nucleons and it's not very stable, so the nucleons actually can separate pretty easily. And the alpha emission, it consists of alpha particles, which are made of 2 protons and 2 neutrons, and they have a very short range, so they look something like this. And 4 nucleons in total, because two protons, 2 neutrons. And now let's move on to beta minus emissions, and this usually happens in neutron-rich nuclei, where a neutron turns into a proton, and an electron is released, so or a beta particle, so an electron, high-speed electron is released, and also a antineutrino is released as well, which is a smaller particle. And neutron turns into a proton and emits an electron and an antineutrino. So this is basically beta emissions. And the antineutrino, so what it is, it carries away some of the momentum and energy, but it has no charge. And neutrinos were hypothesized due to observations of beta decay. So they realized that the energy after was smaller than the energy before, so energy had to go to somewhere, but they didn't know where. If it only decayed with a beta particle or just an electron, because that's what they thought at the time. They didn't know neutrinos existed. So Pauli suggested that a smaller particle of little to no mass would take the rest of the energy away, so the antineutrino of the beta decay. Now let's move on to particles and antiparticles. So let's go into a photon. So a photon is a packet of electromagnetic radiation. So say you have light or electromagnetic radiation, a photon is like a small packet of it. So the smallest of that you can get from if you try to split it up, split light up into packets. And the electromagnetic spectrum is a continuous spectrum of all possible frequencies of light, basically. So you can have higher frequencies, lower frequencies, and that's the spectrum. So from higher to lower, and you can get any frequency that you like. It's a continuous spectrum, as you can see. And we can calculate the energy of a photon by using Planck's constant times the frequency, or Planck's constant times the speed of light over the wavelength of the photon, or the light that the photon, or the frequency that the photon has, so the wavelength as well. And this equation is to find the energy, and as you can see, h is the Planck's constant, f is the frequency of the electromagnetic radiation, so therefore it's also the frequency of the photon, and c is the speed of light, and lambda is the wavelength of the electromagnetic radiation, which is also the wavelength of the photon as well. And every particle has an antiparticle. They have the same rest mass, which we'll know what this is later, and the same rest energy. So rest mass is just basically the mass of the particle or antiparticle, and because they have the same rest energy as well, so the particle and the antiparticle have the same rest energy, the energy is related to the mass, or the rest energy is related to its mass because of E equals mc squared. As you can see, you have E, which is the energy here, and m, which is the mass here. So they're related, and c is, by the way, the speed of light, which is constant. So you can see you can relate energy and mass. So rest energy is related to the mass. So they have the same rest mass, same rest energy, but they have opposite charges. So here we have a table which tells us about particles and antiparticles. So say we have the particle and antiparticle here. So we have a proton, antiproton, neutron, antineutron, electron, positron, which is the anti-electron basically, and you have a neutrino and antineutrino. And here are the symbols. So when you have an antiparticle, you normally add this dash on top. As you can see, antiproton, antineutron. I mean, this one's E plus because it shows the charge, so E minus becomes E plus, and then you see that dash on top of the neutrino symbol. And as you can see, the charge of a proton is +1, so the charge of an antiproton has to be -1. The charge of a neutron is 0, and the opposite charge of 0 would be 0, so the antineutron would also have a charge of 0. The electron has a charge of -1, so the positron must have a charge of +1, and the same as the neutron for the neutrino, because you have 0 charge, the opposite of 0 is 0. And here we have the masses, so we have an extra decimal place of the masses that you can see is slightly different for the proton and the neutron. You have the 3 and the 5. And same for the electron. And you can see they all have the same mass. For the protons and the antiprotons have the same mass. The neutrons and the antineutrons have the same mass. And the electrons and the positrons have the same mass as well. And the rest energy, which is related to this mass, is the same for proton and antiproton, neutron and antineutron, and electron and positron. And because we don't know the masses of the neutrinos, we just say they're 0 for both of them. So as you can see, they're the same, and this relates to the mass that they have, each of them. And as you can see, the particle and antiparticle do have the same rest mass, and they do have the same rest energy. And yeah, neutrinos have zero mass or negligible mass because we don't know yet. So relative charge of 1, so when they say you have a relative charge of 1, so for example a proton is +1, an electron is -1, is the same as 1.6 times 10 to the minus 19 coulombs. And just remember the coulombs symbol, so this is the SI units. And when it says mega electron volts from before, from over here, from the rest energy, you can, this MeV is mega electron volts, that's what it stands for basically. And it's just a unit for energy on smaller scales. And 1 electron volt, so mega would be 1 million of these electron volts, is the same as 1.60 times 10 to the minus 19 joules. So the same number here, but instead of coulombs, you have joules. And remember so for the mass, the SI unit is also kilograms, so this is in kilograms, by the way. And this is the symbol of neutrinos, so don't confuse it with the EV, it's VE. And the small e at the bottom is for electron, stands for electron. This means that if you see VE, this is an electron neutrino, because you could have V something else, for example, V mu, which is a Greek letter, that means it's a muon neutrino, so it's slightly different, because we'll learn later about lepton numbers, and we'll look at that later. So now let's move on to creating matter from energy. So you can create matter from energy because of the formula of E equals mc squared from Einstein's special theory of relativity. And you can turn energy into matter and matter into energy. And these are, you can go either way. And so rest energy is the energy if all the particles' mass was converted into energy. So the rest energy of the particles that we saw before, so say this rest energy, is if you converted all this mass into energy, you would get this much energy at the end. So that's how it relates. And when you convert energy into mass, you're going to get matter and antimatter. So both have to be created when you go from energy to mass. And this is done through pair production. So for example, you can have a collision between two protons, so a proton here and a proton here, are going at very high speeds together. When they collide, energy is converted into more particles. As you can see, when you collide them, you get a new antiproton and a proton being created. And any excess energy is converted into momentum. And so you can do pair production. So as you can see, it's called pair production because you have a proton-antiproton pair created from high speed, which is basically energy, so energy into matter. And you can also do pair production from a photon, where you have a photon which needs a high enough energy to pair produce. So it would be like a gamma ray, because gamma rays usually have the highest energy photons. So it has a really, really high frequency. And when it has a really high frequency, it has a chance of splitting into an electron and positron pairs, which is pair production because you have the electron and the positron of the particle and antiparticle. And the electron positron pairs are caused because they have low rest energies, so that as soon as the gamma ray has enough energy to pair produce, it will just produce electron and positron pairs. And this usually happens near the nucleus of the atom. And when you look at pair production, you can make a conservation of energy equation where you have your minimum energy of a photon. So when you have the photon over here, to find this energy that it has, minimum energy, so the energy of the photon is equal to the final energy of the outcome, which is the rest energies of the electron and the positron. So because you have an electron and a positron, you will have to multiply by 2. So the rest energy multiplied by 2 is the same energy that the photon would need to have. So the minimum energy that the photon would need to have. And to find the frequency of that photon, you'll just use HF from the equation that we found before of E is equal to HF to find the energy of a photon. So using this equation, you can find the minimum energy of the photon required to pair produce 2 electrons and an electron and a positron. And you can also find the frequency using Planck's constant and you can use this equality, for example, or this equality, or this one is equal to this one to find out what the frequency is or the energy. And now let's move on to annihilation. So this is basically the opposite of pair production. When you have a particle and antiparticle meet, their mass is converted into energy. So antiparticles exist for a very short time because there's so much matter or so many particles, non-antiparticles in the universe, that they will eventually meet a particle and annihilate. So when an electron, which is very common, and a positron, which is not that very common, when they meet, they produce 2 gamma rays like this. So this is why antiparticles are not very, they exist for a very short time, because they will meet a very common electron, which you can find anywhere basically, and they will annihilate and create gamma ray photons. And then we'll make an equation for annihilation as well, where you have the final energy. So the initial energy would be the rest energy of the positron plus the rest energy of the electron, and then is equal to the final energy of the photons, which is 2 photons. So 2 times rest energies is equal to, because remember the rest energy of an electron is the same as the rest energy of a positron, so 2 times rest energy is equal to 2 times the energy of each photon, because you have 2 photons. So if you cancel out the 2's on each side, you'll get the minimum energy of a photon is equal to the rest energy of either one of these. And this is equal to HF, so you can find the minimum frequency of each of these photons. And this is the conservation of energy equation for annihilation. So now let's move on to forces and exchange particles, where forces are caused by exchange particles. Because you can't have instantaneous action at a distance, there must be exchange particles. So you can't have 2 atoms really far away and having forces, so one causing a force to the other, if they're far away, because atoms don't really touch. So you need exchange particles to be exchanged between them for there to be force to be applied. Exchange particles are also called gauge bosons or virtual particles, and they exist for a very short time. They are transferred between particles when a force acts between them. So as I said before, if you have 2 atoms, if one applies a force to another, there is a virtual particle or a gauge boson or exchange particle which is transferred between the 2 atoms. And you have 4 fundamental forces in physics these are actually fundamental. So any other force is a combination or a version of these forces. So you have the electromagnetic force, which exchanges virtual photons between each particle when each particle experiences electromagnetic force, and the particles that are affected are charged particles. So the charged particles are the only ones to be affected by the electromagnetic interaction, and these exchange virtual photons between the charged particles. Then you have the weak interaction, where the gauge boson or the exchange particle of the weak force is the W plus, W minus, and the Z0 bosons, and they affect all particles. The strong nuclear force affects all hadrons, and the exchange particles can be either pions or gluons. And we'll go into more detail in which one is used later, and also for the weak force, which one of these are used. And then for the gravitational interaction, there is the hypothesized graviton, which is not discovered yet, it's just been hypothesized, and it affects all particles with mass. So it wouldn't affect photons because photons don't have a mass. And yeah, for particle physics, you don't really take into account gravitational interaction because it's so small on the small scale of particle physics that you can say it's negligible. So the strong nuclear force, as we said before, you can have either gluons or pions as the exchange particle. And gluons is when you have the strong nuclear force between quarks inside of baryons, for example, or mesons, and the pions are exchanged between baryons themselves. So as you can see in the nucleus, the pions are exchanged between the protons and the neutrons to have the strong nuclear force hold the nucleus together. And you have let's look at the range of each interaction and the relative strength of each interaction of the four fundamental forces that we looked at before. So the strong nuclear force has a relatively small range of 10 to the minus 15 meters, which is very, very small. And its relative strength is 1. And so this will be we'll compare everything to the strong nuclear force for the rest of the relative strengths. And the electromagnetic force the interaction has a infinite range because photons can travel infinite distance, and the relative strength is 10 to the minus 2 compared to the strong nuclear force. And then we have the weak interaction, which has a range of even smaller than the strong, which is 10 to the minus 18 meters, which is incredibly tiny. And it has a relative strength of 10 to the minus 7 compared to the strong force, so very weak. And then the gravitational has an infinite range, but also has a very, very weak strength, 10 to the minus 36 compared to the strong force. And this makes sense because on small scales, you don't even notice gravity. For example, you wouldn't notice the gravity between a rubber and a pencil, but on big objects like the Earth and the Sun, you realize it. And again, it goes to infinity, so it's a very large range, while the weak and the strong have a very limited range. The larger the mass of an exchange particle, you have a lower range. So for example, the W bosons that we said before, over here, these ones from the weak interaction, these have 100 times the mass of a proton. So therefore, they have a really short range. And therefore, they have a shorter distance between the interaction, and a lot of energy is needed to exchange these bosons because they have so much mass. So therefore, when they interact, the interaction takes a short amount of time because you have a short distance and a lot of energy required, so you wouldn't have that much energy, so it would only go a short distance. And because the photon has a zero mass, so looking at our rule from before, that larger the mass of an exchange particle, you have a lower range. Because a photon has zero mass, so you have no mass whatsoever, it would have an infinite range, so it would have a really large range. So now let's move on to Feynman diagrams, so carrying on from what we did before of exchange particles, but now we get to actually show them in graphs or these diagrams that are called the Feynman diagrams. So the gauge boson or the exchange particle is shown in wiggly lines in the Feynman diagram, and other particles are shown in straight lines. And time always goes upward. This is so useful to remember when doing your Feynman diagrams. And baryons and leptons can't cross the sides. So for example here, remember the straight lines show the other particles and the exchange bosons are the wiggly particles. So in this case it's the virtual photon. And the baryons, for example, the protons here, they don't go to the other side. So say it's split by the gauge boson or the exchange particle, the proton can't jump to this other side, so it has to stay on this side. And as you can see, time always goes upwards. So this is the same proton as this one, and this one's the same as this one, and they are repelled. So they have an electromagnetic interaction between them. They have experienced the electromagnetic or electrostatic repulsion. So because there's a force going on, you need a exchange particle, which in this case is the virtual photon, because of, we said before, the electromagnetic force has a virtual photon as the gauge boson. And the W bosons carry charge. So as you can see in this one, there's no direction, but when you do have a W boson, whether it's W plus or W minus, it carries the positive charge or the negative charge. And that's like saying, so if you have W plus, that which goes to the left, it is the same as saying W minus going to the right, and vice versa. So we can see some examples here later on of when we use the W bosons. So first let's look at the electromagnetic interaction or the repulsion between two particles. So the same example we had before with the protons looks something like this. Remember, time always goes upwards. And the same with electrons, because negative and negative repel. So you would have really similar interaction as the proton because they repel. And they have to exchange a virtual photon, which in this case doesn't really matter the direction. So you don't need an arrow. But if we look at an example of electron capture, which is when an electron falls into the nucleus and is merged with a proton, you get a neutron and a electron neutrino. And this is, let's draw a diagram. So you have the proton, which goes in, and the electron that goes in as the input. So this is the initial part of the time. And then what comes out at the end, so later on in time, so that's why it goes up, time goes up, you end up with a neutron and an electron neutrino. And as you can see, you start with a proton, which is +1 charge, and you end up with a 0 charge. So that means +1 charge is taken away from this side of the Feynman diagram. So you need the W plus boson to carry the charge to the other side, where you started off with a -1 charge and ended up with a 0. So -1 plus that 1 that came from the left side, you're going to end up with 0 charge. So -1 plus 1 is equal to 0. So that's how you can see the charge is transferred from this side to this side, while the particles stay on each side, so they don't change sides. And we can show that this is the same as the other way, because this is the same thing, but now instead we have a W minus boson going to the left. So we have the -1 charge, so we carry the -1 charge to this side, +1 of the proton, so you have proton +1, and then you have the -1 from the electron, or carried by the W minus boson, so +1 -1 is equal to 0, so the charge of the neutron is 0, and then because you're taking away the -1 from this side, you're going to be left with 0 over here, because the minus charge is taken to the other side. So this represents the same thing, but can be represented differently depending on the direction of the W bosons and whether it's plus or minus. Now let's look at beta plus and beta minus decay. So we have beta plus decay over here, where a neutron turns into a proton and releases a so this is beta minus, sorry. So you have a neutron turns into a proton and releases an electron plus an antineutrino or anti-electron neutrino. And the neutron goes in, and because time goes upwards, you have your products as your proton, and then what is released is the electron and the antineutrino. So as we can see, we have a 0 charge here, and then we end up with a +1 charge. So that means either charge is added this way, but it can't be because time is always going upwards. So instead, charge is taken away from the neutron. So a negative charge is taken away from the neutron. So you're left with a positive charge, because 0 minus 1 is equal to 0 minus, so take away -1 is equal to +1. So -1 is equal to a +1. And then you have a negative charge somewhere here, which is left in the electron, and the neutrino has no charge. So this is for beta minus decay. And for beta plus decay, where you have a proton which turns into a neutron, and you have positron and the electron neutrino left, the proton turns into a neutron, and the charge is taken away by the W plus boson, and ends up in the positron up here, and the VE has no charge, the electron neutrino. And this is to show that the charge in the reactants and the products is conserved. As you can see, there's only one positive charge here and one positive charge here, as the rest are neutral. So now let's move on to baryons. So baryons are protons and neutrons, and other baryons exist, but they are very short-lived. For example, you might see, even in the exam, they might ask you about this baryon, but you would have to problem solve to find out what its quark structure and other things about it are. And a proton is the only stable baryon out of all of them. Not even the neutron is a stable baryon. And all baryons decay except the protons, and all baryons decay to a proton. So for example, a neutron decays into a proton through beta minus decay, and this happens through the weak interaction, and it happens when there are more neutrons than protons in the nucleus, but it can also happen when a neutron is alone, and this is what makes the neutron unstable. So the neutron will turn into a proton and do beta minus decay. And then you can also have antibaryons, which are antiprotons and antineutrons. These are not found in nature, just like any other antiparticle or antimatter. And they annihilate when they meet their corresponding particle or anti-antiparticle. So the antiproton meets a proton, they will annihilate. An antineutron meets a neutron, they will also annihilate. So now let's move on to the baryon number. The baryon number is just the number of baryons you have in an interaction. And each baryon has a baryon number of, you guessed it, +1. And antibaryons have a baryon number of -1. So keep that in mind, that antibaryons have a negative baryon number, so -1. And every other particle that isn't a baryon has a baryon number of 0. And the baryon number is actually a quantum number that must be conserved in any interaction. As you can see in beta minus decay, for example, you have a neutron, which is a baryon, a proton, which is a baryon, and neither of these are baryons, these are leptons actually. You have E minus plus the anti-electron neutrino, antineutrino, which is so an electron and an antineutrino, which are both 0 in the baryon number. You have 1 in the reactants, so baryon number of 1 in the reactants, and baryon number in total in the products of 1. So the baryon number is 1 on each side, so the baryon number is conserved. So this is actually a possible interaction. That's why we do have beta decay in nature. Now let's move on to mesons, where you have two types, where one of them is called pions and the other one kaons. And they all have a baryon number of 0. And because they are quark-antiquark pair. And pions look something like this, and kaons something like this. You have the pi symbol to represent pions and the k to represent kaons. And they were discovered by cosmic rays and in cloud chambers because they interact with baryons via the strong nuclear force. And now if we recap on all the hadrons we've learned, so we need to know that all the hadrons feel the strong nuclear force. So this is very important. And they are made of quarks, so they're not fundamental particles. No hadron is a fundamental particle. And there are two types of hadrons. One is the baryons, and the other one's the mesons, where the baryons have 3 quarks and the mesons have 2 quarks. And this diagram will help you to understand each type. So you have the hadrons, which split into baryons and mesons, and there are types of baryons, which are the nucleons, the protons, and the neutrons, and you have other types, for example, the sigma, and you have mesons under the hadrons because they are types of hadrons, and you have 2 types of mesons, which are the pions and the kaons, and then you have other types, which we don't have to go into for A level. And now let's move on to leptons. Now we've done hadrons, we can move on to leptons. So leptons actually don't feel the strong nuclear force, so only hadrons do. And these leptons are actually fundamental particles. For example, an electron is a type of lepton, and the electrons are stable leptons. But there are other types of leptons, for example, muons, which is is similar to a heavy electron, so it's just an electron with more mass. And each lepton has its corresponding neutrino, which is also a lepton. So, for example, the electron has an electron neutrino, the muon has a muon neutrino, and the tauon has a tauon neutrino. And neutrinos have almost zero mass and zero charge, and they only take part in weak interactions. They could pass through the Earth without anything happening to it. So that's how little they interact with matter. And for lepton numbers, they have to be conserved, but you have to count each lepton number type separately. So for example, electrons have their own lepton number, muons have their own lepton number, and tauons have their own lepton number. So different lepton numbers, Le, L mu, or L tau, that are conserved separately. So they need to be conserved separately. So for example, you have, say, the name of the lepton, the symbol, and the lepton numbers over here, and the charge of each one, just to know. So for example, the electron has a lepton number or electron lepton number of +1, and the electron neutrino has also a +1 for the electron lepton number, while the positron and the anti-electron neutrino have both negative electron lepton numbers, while for the other types of lepton numbers, they have 0 because it's not a muon or a tauon. So all of these have these for the electron lepton numbers. And the charges of an electron, you know, is -1, 0 for the neutrinos, and +1 for the positron. So now let's look at the other types of lepton. So here you have the muon. The muon has a positive lepton number for the muon, so a muon lepton number of +1, and the muon neutrino as well. And the antimuon and the antimuon neutrino have both muon lepton numbers of -1. And the charges of a muon is -1, and antimuon is +1, while the neutrinos have no charge, as we said before. And now for the tauon, it has its own lepton number over here, and a tauon has a lepton number of +1. The tau neutrino has +1 as well, and the anti-tau and the anti-tau neutrino have -1 lepton numbers for the tauon. And the tauon has a charge of -1, and the anti-tauon has a charge of +1, while again the neutrinos have a 0 charge. So now let's look at all the conserved quantities in particle interactions. So you have charge, the baryon number, the lepton number. Remember, you have to look at each one of these separately. So each lepton number is conserved separately. So for example, you can't have electron lepton number of 1 on one side and then 0 on the other side while having a muon lepton number of 1 on the other side. So it needs to be 1 on both sides for electron, 1 on both sides for the muon, and 1 on both sides for the tauon. So that's how you conserve lepton numbers. Then you need to also take into consideration the strangeness, which is conserved in all interactions except the weak. The weak interaction, the strangeness decays in the weak interaction, so it is not conserved, only in the weak interaction. And also, momentum and energy are conserved quantities, as we know from mechanics and GCSE physics as well, but they're not really usually taken into account for particle interactions or particle equations or interaction equations. So now let's move on to quarks. So quarks are fundamental particles. They are the building blocks for hadrons, as we said before. Hadrons aren't fundamental particles. They are made up of these quarks. And you have the up and the down quarks. Weird names, I know, but these quarks make up the protons and the neutrons in the nucleus. And then you also have a strange quark, which has a property called strangeness. As we said before, it is a quantity that must be conserved in every interaction unless it's the weak. And this is a quantum number and is conserved only sometimes, as we said before. And strange particles are created by the strong interaction and decay by the weak interaction. But strangeness has to be conserved in the strong interaction. I know they said they were created in the strong interaction and decay by the weak, and because in the weak it's not conserved, you could assume that it's not conserved for the strong, but it is actually. It has to be conserved for the strong because in strange particles, when they are produced, they come in strange anti-strange pairs, which have a strangeness of +1 and -1. So you can actually start with a strangeness of 0 on one side and 0 on the other side while still having strange particles, because you'll have a strangeness of +1 and -1 on the other side, which cancel out to make 0. So it has to be conserved in strong interactions. And here we have a table of the quarks, all the types of quarks, with their symbols, their charge, so relative charge, their baryon number, and their strangeness. So you have the up, down, strange, and their antiparticles, the anti-up, anti-down, and anti-strange. And remember, you add the dash on top to make them strange. And these are the symbols, U, D, and S. And the charge of an up is plus 2/3 relative charge. So if a proton has a relative charge of 1, the up quark has a charge of 2/3, and the anti-up is minus 2/3. So the down quark has a charge of minus 1/3, and the anti-down has a charge of plus 1/3. So the up has 2/3, and the down has minus 1/3. And this strange quark has a charge of minus 1/3, and the antiparticle always has the opposite. So as long as you memorize this, this, and this, you can just apply the negative to find the antiparticle, and it should be pretty easy. So just memorize the up, down, and the strange charges. So 2/3 for the up, and minus 1/3 for the down, and minus 1/3 for the strange. And the baryon numbers are all 1/3 unless they're antiparticles, so 1/3 for up, 1/3 for down, and 1/3 for strange. And the antiparticles have minus 1/3, minus 1/3, and minus 1/3. So they all have a third for each baryon number. And strangeness, so here's the weird thing. Strange particles actually have a strangeness of -1. I know you would expect +1, but it has a strangeness of -1. And anti-strange particles actually have a strangeness of +1. So just keep this in mind, that it's -1 for the strange, and anti-strange particles have a +1. I don't know why. That's just how it is. That's how they've made it. So that's just a convention. So now let's move on to quarks in baryons. So in baryons, they look like this. As we said, they have 3 quarks. And if you calculate the charges from before, you realize that they do cancel out. So remember, up is 2/3 and down is minus 1/3. 2/3 plus 2/3 minus 1/3 should add up to a charge. So you can find out whether this is a proton or a neutron. So 2/3 plus 2/3 is 4/3, minus 1/3 is 3/3, which is 1. So you have a charge of 1, so this must be a proton. And quarks are discovered by baryons, electron scattering experiment. So very similar to the Goldfield and the alpha particle scattering experiment they did to find nuclei in atoms. They did similar to find the quarks inside of the nucleons. So they scattered electrons and found the quarks. And baryons are made up of 3 quarks, as we said before. And the proton is made up of up, up, down, as you can calculate using this table over here, the charge, and the charge should end up as +1 for this one. And then you have anti-up, anti-up, down for an antiproton, which is just anti of every quark inside of here. And this should end up as a charge of -1. And then for a neutron, you have down, down, up, or UDD, and you can use the table again, this table over here, to calculate the charge of a neutron. So you have minus 1/3, plus 2/3 should add up to make 0. And then when you have an anti-neutron, you have just basically the same as a neutron, but all anti-quark, so anti-up, anti-down, anti-down. And now let's look at quarks in mesons. So mesons are quark-antiquark pairs, where pions are made up and down quarks, while kaons have strangeness in them, so they have to have a strange or anti-strange quarks. And pi minus is the antiparticle of pi plus, for example, and k minus is the antiparticle of k plus, so K minus and K plus are antiparticles, and pi naught and K naught are the antiparticles of themselves. And imagine in this box you put a pi or a K. If they have a plus at the top, a 0 at the top, or a minus at the top, they either have a charge of +1, 0, or -1. And yeah, you can either put pi or K in these boxes. So this power tells you the charge, basically. So if we look at the strangeness of each meson, we can see that if we have particles with strangeness of 1, 0, and -1, we can categorize these types of mesons. So with a strangeness of 1, we have to have only kaons, because kaons have strangeness. And you'll have K plus, which is made up of U and anti-S, and K naught is made up of D anti-strange, so down anti-strange, and this one's up anti-strange, down anti-strange. And by the way, you don't really have to memorize this. As long as you know the charges, you can see what they end up as, and say this one ends up as +1, so a charge of +1, you can actually guess that it's a plus of something, and if it has strangeness, it has to be a kaon. And say the strangeness is 0, this is where you have the pions, where you have no strangeness. You have up anti-down, and if you find the charges, it should end up as +1 charge, so you can guess it's the pi plus. And then you have the pi naught, which is either a U anti-U, or up anti-up, or a down anti-down, which if you add up the charges of this one or this one, you should get 0. So that's how you can tell it's a pi 0, because it has no strangeness as well. That's how you know it's a pi. And for the pi minus, you have a down anti-up, and if you find the charges of these and add them together, you find that it's a -1 charge. So you can guess it's a pi minus. So you don't really have to memorize this, just look at the charges of each one and see whether they have strangeness or not, and you can actually find out the type of meson it is. And for strangeness of -1, you have a strange anti-down. So this is for the anti-K naught particle, or the meson. And this is, so one is down anti-strange, then this one's strange anti-down. And remember, because strange particles have a strangeness of -1 and anti-strange particles have a strangeness of +1, it's in this order here. So this is the antiparticle, and then you have a strangeness of S, so strange strange particle and a anti-up particle together, they create the K minus particle. And again, you can check the charges, and they should make a -1. So that's how you know that it's a K minus, because it has strangeness and it has a negative charge. So now let's move on to the properties of quarks. So the weak interaction changes the quark type in the baryons or mesons. And for example, if we look at beta decay, when a down quark turns into an up quark, or remember we said a neutron turns into a proton and then releases an electron, an antineutrino, it's the same but with quarks. So we look at the quark types, we've got down, down, up. When we go through beta decay, which is a weak interaction, we end up with up, up, down. As you can see, the quark flavors change. So a down quark turns into an up quark. These two stay the same, by the way. And you're left with the same lepton products, so the antineutrino and the electron. And let's look at beta plus. And this is when an up quark turns into a down quark. As you can see, you have the up here, turns into a down. And these two stay the same, by the way, so nothing really happens to these two. And a positron and a electron neutrino is emitted. So this is the same as so proton turning into a neutron is the same as a up quark turning into a down quark, but this is just more specific way to describe it, or describe beta plus decay. And you can never have quarks alone, because if you supply enough energy to separate quarks, you're going to have this new energy that you've used to separate the quark is going to be converted into a quark anti-quark pair, which is a meson basically. And this is pair production actually. and this makes new mesons. So say you have a proton over here and you try to give so much energy to this quark over here to try pull it away from the proton structure to try make it by itself, you accidentally give so much energy to the system that it ends up making a quark, so an up anti-up pair, and here you're left with a pi naught or a pion with a 0 charge and the proton still there. So you can't really separate protons by themselves or quarks by themselves, because they're just gonna keep producing pairs, so they're never alone. So quark confinement is not possible because of this case. And we're still looking for new particles, not me, but a lot of scientists out there are looking for new particles. And because there are new theories to explain observations made in experiments, and then you carry new experiments out to prove your new theory or your new particle that you have theorized. And if it exists, you validate it. And you have particle accelerators, which are very expensive, which are used for these experiments to find new particles, to prove new particles, or to look at observations of how particles act. And these are very expensive. So you have large groups of scientists and engineers which collaborate together to fund experiments and just look at the data and try to find new theories and try to understand how particles work further. So we can actually learn a lot about what we're made of and what these useful particles might help us to do in the future. So this is the end of the video. Thanks for watching. I hope this was useful for you.